back, and we're going to be looking now at finding the inverse of a 2 by 2 matrix. All right. Now, before we actually get into an example, I just want to point out very importantly that first and foremost, that if a matrix is called A, then its inverse is denoted like that. So it's an A with a -1 superscripted, which means the inverse of A. Similarly, if a matrix is called B, then its inverse is denoted like that with the B and -1 superscripted. If a matrix is called C, then its inverse is denoted like that. So once you see this denotation, you know it means the inverse of matrix B. This means the inverse of matrix C. This means the inverse of matrix A. Okay? All right, let's move into our first example. Before we actually look at the first example, let's just look at the formula that finds the inverse of a matrix. So the inverse of matrix A would be equal to 1 over the determinant of A times adjoint. So the inverse of a matrix is equal to 1 over the determinant times the adjoint of matrix A. So this is the formula that allows you to find the inverse of a matrix, and this is the formula that we're going to be using to determine the inverse. So of course, if this was B, to be B to the -1 equals 1 over the determinant of B times the adjoint of B. All right, but that's the formula that finds the inverse of a matrix. All right, here's our first example. And again, we're only dealing with 2 by 2 matrices, so it makes life very, very straightforward when you're thinking about inverse at this level. Okay, so first and foremost, based on the formula, and I'm just going to write the formula over here, so that kind of stands out a little bit. So it's matrix A, so the inverse of matrix A is going to be equal to 1 over the determinant of A times the adjoint of A. Now remember, it is 1 over the determinant. So when you find the determinant, it's 1 over the determinant. So in order to find the inverse of matrix A, obviously we need to find the determinant first and then find the adjoint, and you know how to do that already. So again, elements in the leading diagonal would be this. Always remember that. So the first thing we need to find is the determinant, and the determinant is equal to the product of the elements in the leading diagonal minus the product of the other two elements. Simple as that. So what we have here is -6 minus -1 times 8 is -8. So that what we have here is -6 plus 8, and that will give us a determinant of 2. So we know what the determinant is. It is 2. The next thing we need to find is the adjoint. And the adjoint of matrix A is simply, we're going to interchange these two elements, 1 and -6. So -6 comes here and 1 goes there. And these are going to stay at the same position, but we're going to change the sign. So this becomes -8, and that becomes +1. So we have the two things that we need to find the inverse, or the two things that we need to use in the formula over there. So we have the determinant, which is 2, and the adjoint is this. So all we need to do now is to get into the formula and proceed to find our inverse. So the inverse is equal to, remember it says no 1 over. So 1 over the determinant, and the determinant is 2. So that would give you 1 over 2, which is a half. So don't forget that it's 1 over the determinant. Now the determinant, 1 over. So whatever the determinant is, it's going to be 1 over, because this is the formula. So we have 1 over 2 times the adjoint, and the adjoint is this matrix. So this would be -6, -8, 1, and 1. So all we need to do is scalar multiplication. Each of these 4 elements will be multiplied by a half. So this is simply a half times, if you want to do it this way, and emphasize that the elements can be written as fractions, you can go ahead. So this would simply be a half times negative 6 over 1, a half times negative 8 over 1, a half times 1 over 1, and a half times 1 over 1. Some of you don't need to do that, that's fine, but I'm just doing that for emphasis. So our final answer will be, of course, when you're multiplying fractions, you multiply numerator by numerator and denominator by denominator. So 1 times negative 6 is negative 6 over 2. Obviously, that has to be broken down. And a half times negative 8 is negative 8 over 2. Now, obviously, I could have said a half of negative 6 is negative 3 already. Half of negative 8 is negative 4. But the reason why I'm doing this is when it becomes a little bit more complicated, you can go ahead and use the same principle here. But you can just say half of negative 6 is negative 3, half of negative 8 is negative 4, half of 1 is a half of 1 is a half, and that's fine. But I'm just doing this because when I teach using the method that is going to work with everybody right off the bat. And a half times 1 over 1, numerator times numerator, so that is a half, and this is also a half. So let me see if I can squeeze it here. The final answer would be negative 3, negative 4, a half, and a half. So you can just look at that. And that is what the inverse is going to be. Obviously, I've run out of space here. So I've written another line saying the inverse is equal to this matrix. So what we found is that the inverse is equal to negative 3, negative 4, a half, and a half. So you can clearly see that we found the determinant, which is 2 here. Product of the elements in the leading diagonal, that give you negative 6, minus negative 1 times 8, negative 8. Negative 6 plus 8 is 2. The adjoint, switch these elements, and then leave these alone but change the sign. And then use the formula, inverse equals 1 over the determinant times the adjoint, which is what we did. A half of negative 6 is negative 3, half of negative 8 is negative 4, half of 1 is a half of 1 is a half. So this here would be our final answer for the inverse of matrix A. Now, very importantly, now, it is always important when you find the inverse, which is this, to show that the inverse is actually correct. Now, you don't have to, but the final thing that we're going to be doing in matrices, which is solving simultaneous linear equations, you're going to have to know how to find the inverse, which is what we did here, and make sure that the inverse is correct before we can use it to solve any simultaneous linear equation. We haven't reached that bridge yet, but there's always a way to check if your inverse is correct, right? So even though this would be a final answer, because you want to ensure that you get the full marks, you can check to see if your inverse is correct, and this is how you do that. All right, guys, and this is what we need to do to prove that the inverse is correct. So basically, if you take the original matrix, which is A, and multiply it by the inverse that you got, you should always get the identity matrix, and the identity matrix is 1, 0, 0, 1. All right? So by simply multiplying the original matrix by its inverse, you should always get the identity matrix, which is that. So what do I mean? So what I'm going to do is take the original matrix, which is 1, 8, negative 1, negative 6, and multiply it by the inverse that we got. And if this guy here is correct, then you should always get this matrix as the answer. If you don't get this matrix, then it means that the inverse is correct, because obviously it couldn't be the original matrix because that's what they gave you in the question. So it would mean that the inverse is correct if you don't get this. If you get this, then it means that this guy here is good. So let's test and see if our answer is correct. I'm going to be using a fine point pencil because I need a space. All right, so the original matrix is this. So I'm going to just take the original matrix, which is 1, 8, negative 1, negative 6, and multiply that by the inverse that we got, which is this, -3, -4, a half, and a half. So if this inverse is correct, then when I multiply this 2 by 2 matrix by this 2 by 2 matrix, this is what I'm supposed to get. If I get this, then this inverse here is good to go. If I don't get this, then I have to go back all over again with this process to find the inverse of matrix A. So let's try and see if our answer is in fact good. All right, so again, it's row by column. If you remember multiplying matrices, so it will be 1 times -3 plus 8 times a half. Then over to the next column, same row, next column, so it's 1 times -4 plus 8 times a half. So I hope your skills are good with multiplying matrices. Then all the columns are used up, so we move to the next row and start the process all over again. So it's -1 times -3 plus -6 times a half, and -1 times -4 plus -6 times a half. You take your time when you work this. So this is -3 plus 4, and this is -4 plus 4. And right away, you can see that here, we're going to get this 0 here. You can clearly see that this is going to give us 0, so it looks like I'm on the right track. And also -3 plus 4 is going to give me 1, so it looks like I'm on the right track. And what that is telling me is that there's a good chance that my inverse is actually very, very correct. So let's continue it down here. -1 times -3 is +3, plus -6 times a half is -3. Looks like I'm going to get 0 here, which is this here. And if I get 1 here, then I'm pretty confident that my inverse is correct. So -1 times -4 is 4, plus -3. And this is going to give me -3 plus 4 is 1, -4 plus 4 is 0, 3 plus -3 is 0, 4 plus -3 is 1. And this is the identity matrix here. So this is telling me right away that the inverse, which is this here, is correct. So this gives me the confidence that my inverse is correct. All right. So this is optional unless CXC asks you to do it, but obviously doing paper 1, so they wouldn't. But this procedure here allows me to test the inverse that I got, multiplying the original matrix by the inverse. And if I get the identity matrix, which I did, it tells me that my inverse is correct, which means the solution here that I did to find the inverse of matrix A, which is resulting in that, was indeed correct. All right, I hope you guys found this video insightful, and I'll see you guys on the next video.